My name is Adam Barker. I'm with the Buddy School of Informatics, Computing, and Engineering at the Indiana University. And I'm here to talk about energy-aware routing with computational offloading for wireless sensor networks. So just a quick primer on, make sure we're all on the same page with wireless sensor networks. Wireless sensor networks, WSNs, their primary function is remote sensing. They typically will gather images, acoustic information, environmental data, RF data. They're typically ad hoc, meaning that there's no fixed infrastructure. They usually form mesh topologies, meaning that data is flowing through the various nodes to get to the final destination. And the other feature is individual nodes tend to be very small, battery operated, low power, small compute capacity, say like an ARM core at the most, or typically a microcontroller. But ultimately, a wireless sensor network's function is to provide raw sensor data that can then be analyzed and used for some ultimate purpose at the end. And as I mentioned earlier, here's a picture of a wireless sensor topology. They're different mobile nodes. They form a mesh topology. But what's key is in typical WSNs, they form there's a fixed destination. As you can see, like different sources will have different paths to get to the ultimate destination. But in the end, the destination, the sink, is usually some less constrained node that has more power, usually is connected directly to the wired internet, so bandwidth concerns are not as much. But this is a typical pattern we see in wireless sensor networks. The wireless sensor network that I'm most interested in, that I focus my research on, is what we call peer-to-peer wireless sensor networks. And this is essentially, you could see this in first responder and military applications. Just like regular WSNs, the nodes are mobile, they form mesh topologies, but the major difference is the destinations are what I consider dynamic. And you can see here you have a source and it's going to the destination in the middle through multiple hops. But then that same destination could become a source of data for another stream, or that same destination could actually be a throughput node going to another destination. So this adds some complexity to the network and allows for different opportunities for routing. So ultimately, the question that we're trying to ask is, can we leverage this network structure to enable information flow? So we have these peer-to-peer mesh networks. They're small devices with limited computational capacity. Ultimately, we want to minimize the time that it takes to get information in the right place, not just raw data, but also the information that is used at the end. We want to minimize the energy consumption, thereby maximizing the longevity of the network, and also maintain all the network quality of service attributes that we can. So looking at the background of research in WSNs, I see it kind of break down into two major categories: network longevity and speed of information flow that I've already briefly discussed. In network longevity, energy efficiency is the primary driver of making sure a network stays active. And we'll talk about that in just a minute. And then we'll follow into speed of information flow, which I've broken down into how quickly we can process the sensor data, and then how quickly we can get data across the network through network traffic control. So looking first at energy efficiency, as I mentioned earlier, wireless sensor nodes typically operate from onboard energy storage, such as batteries. So they're very limited. So ultimately, we're trying to conserve that battery power to ensure the network maintains its longevity as long as possible. So as long as nodes have battery left in them, they're able to gather sensor data, forward packets, and as they run out of battery power and they drop out of the network becomes more sparse and eventually will collapse. So common research approaches for maintaining energy efficiency, one big area is what is considered clustering. And this is essentially where nodes that are of similar distance or similar battery reserves will cluster together and share information within a tight group. And if they're physically closer, ideally they're sending, they're able to send data with less RF power, which requires less energy. There's less retransmitting, so that requires less energy. And ultimately, these clusters allow for more efficient routing of packets. Leech is probably the most popular protocol in this area, where you have cluster heads, which are essentially self-designated nodes that will gather all the cluster members' information and then forward it on over the long haul. And then these clusters rotate over time. Another popular area is max flow algorithms. And these are essentially looking at different methods to use energy as almost like a flow metric, and trying to minimize the energy that's flowing through the network, thereby maximizing the network longevity. Both of these approaches, although they're very common in WSN, they're very difficult to implement in our aforementioned approach, mostly because in a clustering environment, it's usually a very dense network that expects that all the information is flowing to some distant destination. But in a peer-to-peer network, clusters are constantly changing because the destination is constantly changing. Thereby, cluster heads can almost end up being a one-to-one mapping. So you have just as many nodes as you have cluster heads. In that regard, you really have no nodes, or no clusters, excuse me. And then max flow are very computationally efficient algorithms. The challenge is you need to have a model of the entire network at any given time. And with a peer-to-peer network and wireless sensor network, you typically don't have all the information of how many hops you need to get, or how the network looks. So you can't really maximize your flow of energy using those particular algorithms. So from that, we'll look at processing of sensor data as the next metric for peer-to-peer, or for wireless networks in general. And there's essentially two major ways that processing of sensor data happens in a wireless sensor network. So the most obvious and probably the more common is stream all sensor samples over the network. And you can see here, this picture kind of shows it, that you have a node N, and it's sending its sensor stream unfiltered essentially across the network, whatever path it takes, ultimately getting to the destination that then is processing that information to get the result that then will be used for whatever the purpose is. The challenge with this is all those sensor messages generate a lot of traffic, and all the traffic generates more messages, and all those messages come at a higher energy cost. And on top of that, because all these messages are flowing through the network gets congested, and then the bandwidth tends to slow down, and then the network then not only is more costly to operate from an energy perspective, but it's actually getting slower and slower. And the second opportunity, or second method for processing of sensor data, is to pre-process the data locally. So a node will stream its sensor stream to its local processing core, and then it'll pre-process all that information, and then only send the result, which, as far as a network goes, that's much more efficient, because you're sending a fraction of the data, because typically the processed data is only a fraction of the size of the raw data. But the challenge here is this is computationally demanding, depending on what your processing function is. And if we look at a typical wireless sensor node, they're very compute constrained devices. So it takes a lot of energy it takes a lot of computational power in most cases to process this information, which then the more data that the local node is processing, the more time it takes. So thereby the raw data is stuck in this processing loop for a long period of time, and then it delays its opportunity to get to the destination. So that, again, is not ideal. One approach to alleviate this is what is called computational offloading. And that's essentially transferring computational tasks to separate processing nodes that ideally have more processing power. This concept has been popularized in 5G networks, multi-access edge computing, the MEC concept. And there's a lot of research done here. And essentially, this diagram explains it, that a node has a raw sensor stream, and it's going to forward that stream, typically in an MEC environment. It's only just a one hop, so you're not overloading the network too much. And then the MEC is then feeding back the processed result to that node for whatever reason or whatever its use is. A lot of the research and solutions for this typically involve, again, maximum flow algorithms, or even some more advanced things like game theory, looking at finding Nash equilibrium and that kind of thing. But again, this approach requires a stance that we don't necessarily have in a peer-to-peer network, which is a model the complete network, because it's got to be able to understand what streams can be processed at the remote cloud, and where all those nodes are and how much data is flowing. And it's also had to have some sort of central control, which is exactly what is in the case of the MVC cloud. The MVC nodes are actually controlling all the handheld nodes that are out in the environment, and they are the ones directing whether or not to forward raw data or pre-process. So, but again, in a peer-to-peer network, we don't have that central control. So then the last part of research that wireless sensor networks are typically looking at is a network traffic control, and that is really focused on finding the shortest path. And there's many algorithms out there that have been around for 20, 30 years, if not longer. Typical ones you've probably heard of: the ad hoc on-demand distance vector, optimized link state routing, dynamic source routing. And typically these algorithms use some sort of flooding, depending on the algorithm, when and where that flooding takes place. But ultimately, these algorithms are really trying to find available paths, and then maybe optimizing for some user-defined metric. But really their focus is not necessarily on route optimization, it's really on path finding. So they leave the route optimization, what's path to take once you know those paths, up to the individual implementation. So then that leads us into a reinforcement learning approach that was actually developed in the mid-90s by Lippmann and Boyan, called Q routing. So Q routing utilizes a Q learning technique to actually learn optimal routes in a wired network. So if we assume that we already have those different paths to travel, this Q routing algorithm can actually learn which one is the optimal path. And just to kind of give a quick primer on reinforcement learning for those that aren't aware, this is the typical structure we see in a reinforcement learning environment. You have an agent. In our case, that agent is going to be the node, and it has to take some sort of action in the environment. Once it takes that action, it gets some sort of reward signal back, and then it transitions to a new state. So this loop iterates continuously as new actions are taken in this paradigm. In the Q routing algorithm, the agent, as it takes actions, its ultimate goal is to maximize the reward given over the long period of time. That long-term reward is known as the value. And as it takes actions over time and comes across different states, it actually builds up information, and it learns optimal actions to take during different states. And those become known as the Q value. And the Q value is essentially the action that an agent can take in a known state to maximize its long-term reward. In Q routing algorithm, the authors designated one-way delay between neighbors as the reward. So then the Q value is actually the total one-way delay across an entire route from beginning to end. And to kind of just briefly show this, I have a quick example here. In this, A needs to actually send data to B, and it's got two potential routes. It can choose via X or via Y. And ultimately, it learns the optimal route by looking at the Q value of A through X to B is the cost of forwarding, or the time to forward from A to X, and then whatever X's estimate it is to get to B. So every time A sends a packet to X, X responds with its estimate to go to all its other destinations. So it continually builds up this table of what it thinks are the optimal routes. And then ultimately, what A has to decide to do is take the minimum of time between either X or Y. The powerfulness of this algorithm is that it's distributed, meaning that every decision can be made, every routing decision can be made at each individual node individually. Ideally, each one is optimizing its link choices as it goes, thereby ultimately getting the optimized route. So that brings us to our algorithm, the energy-aware queue routing with computational offloading. ECO is what we call it for short. It utilizes the concepts previously discussed of energy efficiency, computational offloading, queue routing. Our ECO is developed for our unique peer-to-peer wireless sensor network use case. Our desirable factors are network longevity and speed of information availability. So the mechanics of it is it's based off the queue routing algorithm. The major difference is it incorporates the ability to perform computation in route, so essentially a form of computational offloading. And this diagram shows it here. So we have this node that is streaming sensor data, and this node actually, using the ECO algorithm, can decide to either compute part of its data locally and forward some of it en route, and so thereby it's trying to make the optimal decision at any given point of whether to compute or to forward that data. And as it forwards raw data, it is each node that is coming across the path or using the data across the path is also looking to make that same decision. So each individual node is making a decision whether it should compute data en route or forward on. So as the raw data traverses the network, it is slowly getting computed, and then the process data is then forward ultimately to the destination, where the destination might get some partial raw data and some partially processed data, and then its job is just to compute the remaining raw data, combine the results to get the actual information at the other end. So when and where to perform this computation is learned by the algorithm. And we've also included some energy cost awareness that biases the learning that we'll talk about in a minute. So again, we'll go back to our example we had before. A needs to send to B. B needs the raw data to be ultimately processed before it is usable. So the action choices are, again, forward via X, forward via Y, but now A can actually choose to compute locally as well. And just like with the queue routing algorithm, each time a packet is sent, each individual node will send back its estimate of what it takes to forward that data on, but that also will include what it estimates it can actually do to the time it would take to compute that segment of data as well. So just like it's learning the time to forward, it's also learning the time for each individual node to compute data. So then the queue table becomes, for forwarding from A, becomes the cost to forward to X, plus the minimum cost between X forwarding to B or X computing, and same with Y. And then the decision process is A has to decide when forwarding to B whether to forward to one of the two routes or actually compute it locally. And that decision is being made continuously as messages are being passed. And just like queue routing, ECO is distributed. Each decision and action is made at each node, and there's no global knowledge of the network need required. So as I mentioned earlier, our algorithm includes energy awareness. As we know, RF transmissions can cost 3 to 5 times the energy than all the other functions combined. So minimizing the amount of transmissions is ideal. So the decisions to transmit versus compute locally include 2 factors: the time it takes, which we've covered with the queue routing algorithm, and then the energy it costs. awareness of what it costs and as far as energy requires some sort of model. So we built a model of what it costs to forward information. And that model has informed what we call an energy factor. And this energy factor essentially biases the cost of transmission based on the current energy stores. This energy factor is tunable for various platforms, RF protocols, and energy storage devices. Ultimately, for our testing, this is the energy factor that we came up with, and it only takes in two requirements: the battery used, meaning how much battery storage is left, and also a factor of what's called mission remaining. So if we understand how long that network has to last, if it's getting towards its end of life, then we can make more, say, riskier decisions and transmit more information more often, because we know that its requirement to continue operating is going to go away eventually. So ultimately, this is what our complete algorithm looks like. And I just want to point out that that here is the energy factor, and that biases actually the cost from forwarding to the next hop. So as it forwards, it's looking at not only the time it takes, but actually that bias of the energy factor, so that influences its decision on how to forward. So based on our algorithm, we did some experimental analysis. We actually built up a wired network of 7 BeagleBone Blacks. A BeagleBone Black is just a small single board computer like a Raspberry Pi, but it runs a full version of Linux. Our lab didn't allow for a full wireless network, so we chose to do wired and then simulate the cost of wireless transmission. We use Ethernet with UDP transport protocol with transmitting messages about 2,400 bytes in length. We simulated sensor data. Then ultimately what we looked at was streaming 750 messages from node 4 to node 1 over multiple different scenarios. All the other nodes in the network were responsible for loading the network with different data. We had 2 different loading scenarios where each node would be sending about 1 message a second, which we called low, and then high, which was essentially sending messages as fast as possible, which ended up being at a rate about 1.5 megabits per second per node. So here's our experimental results. And this is looking at message processing time from end to end. We ran 10 runs and then averaged the cost of, or the time for each of the 750 packets. What you can see here is at the low packet rate, at the low data rate, energy awareness wasn't that big of a factor, even though the eco algorithm really did significantly reduce the time it takes to send messages. But as you get into the high packet rate, as more messages are being sent, the energy factor becomes more prevalent. You can see there's a significant reduction in average speed per message difference between the energy awareness, which is orange, and without energy awareness, which is blue. These results show the total energy cost of our algorithm. And interestingly, at the low packet rate, it was on average a little bit more expensive from energy. This is because our algorithm actually has some exploration built in, which is typical of a reinforcement learning. This exploration allows it to choose non-optimal routes just to see if there's potentially something else that can be learned. So this exploration actually comes at a higher cost. But as you see, when you get into the higher packet rate, energy consumption is drastically reduced using our algorithm by as much as 2/3 of the energy cost. So this was a significant finding for us. This here, I just wanted to show how the energy factor increases or biases the cost of everything as time goes by. So you can see here, you have the 3 different actions. You have forwarding via one route or via another, or computing locally. And this red line here, it just kind of give you an idea of how it slopes upwards, the cost of everything. As time goes by and energy storage reduces, the cost of everything slowly increases, but ultimately the cost of computing locally becomes more favorable. And you can see that here, these tick marks represent decisions that were made, whether green is forward and yellow is compute locally. As you can see, the density of them changes as time goes by and the energy factor biases towards computing locally. So ultimately, what we found is that eco is a viable algorithm in our environment, where both energy efficiency and speed of information flow are critical. It's optimized for this peer-to-peer sensor network that we have shown. It's a simple algorithm, so it can easily be deployed on small devices, typically where wireless sensor networks operate. There is a lot of tuning that can be done on these algorithm parameters that can dramatically affect results, and we're continually researching different tuning things. In our future work, we're looking at trying to expand the action space to look at the effects of not only computing locally, but maybe even store and carry forward, which is a common effect in wireless sensor networks as they lose connection. How those can be optimized, how those decisions can be optimized, and also increasing the state space for more complex quality of service metrics that can be added in. But that kind of leading us towards a deep reinforcement learning approach. And obviously, as we get into deep reinforcement learning, it really becomes a factor of utility versus time, or usability versus time. How long it takes to actually calculate the optimal route, which is how much the time it takes to that we're saving. That's the ongoing research that we have happening right now. So with that, that concludes my talk, and I will take any questions.